Okay, folks, so we'll have a quick check through homework. You had to match up your forms of energy. So number 1 would be thermal or heat. Number 2, gravitational. SEC would never be as ambiguous as this. Number 3, solar or light. Number 4, elastic. Number 5, nuclear. Number 6, sound. Number 7, chemical. So remember, any type of fuel source, so food is a fuel, is chemical energy. Number 8, kinetic. And number 9, electrical. And the other hint is that if there's a wire, then there has to be electrical energy involved somewhere. So in terms of our energy transfers then, first one is electrical to sound. Second one is electrical to thermal energy or heat. Third is electrical to light or solar energy. 4 is chemical, because this is a fuel that's burning and it's being turned into light or heat. Number 5 is sound to electrical. So technically you would speak into this and the wire would take it to a speaker and you would hear that speaker. So it's sound to electrical. And the last one with our plant is taking light energy and it's turning it into food. So that is a chemical food store. This then was our word game, crosswords. So kinetic energy is moving energy. Sound energy is what we hear. In a spring, it's elastic energy. In a circuit, it's electrical, because there's going to be wires involved. From the sun, in this case I wanted light and not solar. Stored energy is potential energy. Wasted energy is always thermal energy, vast majority of the times. More energy at the top of the hill is gravitational. So that's technically potential energy. And number 9 in a battery is chemical, and the word that it made was energetic. So in terms of our gaps, when our kettle is switched on, electrical energy is changed into thermal and sound and light, because we hear the kettle boiling and you may see the light switch go off. When the drill is working, electrical energy is turned into kinetic, sound and heat. When the gas cooker is on, its chemical energy is being changed into thermal energy, into light energy and into sound. So useful energy transfers for these objects. So the things that we want the most is electrical into sound. For our ghetto blaster, for our fan, it's electrical into kinetic. For our iron, it's electrical into thermal or heat. And for our lamp, it's electrical into light. Now there was loads of different pictures here. 7 things that need energy. Nearly everything that isn't a table or a chair needs energy in this picture. So there was loads of things. 5 examples, picked whatever you want, so I've just put some here. So the lamp goes from electrical into light, sound and thermal. The bike is chemical energy, because the person has to sit on it to make it work, and that's getting transferred into chemical, sound and thermal. Our plant does light into chemical and also kinetic energy, because plants will move during the day, they'll follow the light. Candle is chemical energy into light and thermal. A vacuum cleaner is electrical into kinetic, sound and thermal, and hopefully that's given you enough, and you should be able to figure out the computer, the ghetto blaster, the stereo, the fire, if you needed to. So the wasted energy for these pictures, so the ones that we really don't want to get because they're no use to us. So for our ghetto blaster, it's going to be thermal energy. If there's any heat generated, that's useless for this scenario. For the fan, it's again thermal energy. That's useless to us because we want the fan to cool us down. For our iron, sound energy, they will probably be light on it, but sound is a waste. And for our lamp, it would be thermal or sound energy. They are wasted energy because we only want the lamp for light. So if we were in school now, this would be our starter. So with today's lesson, we're going to look at how we show energy efficiency through maths and through diagrams. So we've said here, this has a wire attached to it, so this has to be electrical energy in this little starter, and what it's going to be changed to, it's going to be changed to thermal, and it's going to be changed to light, and there's probably some sound also being made in this one. So here is our torch. So we said a torch has a battery. Batteries are a source of fuel, so they're chemical energy, and it's going to be changed into light as the main one. You will also get some thermal energy is going to be generated, and maybe if your torch is rubbish, you'll get some sound. We would play bingo, but we're not here. Now, you have possibly seen this, you've definitely seen it on electronic devices if you've ever gone into Currys or any of those type of stores. Your house, depending on how old it is, if you've sold it or built it new, it'll have a BER rating, so it tells you how efficient it is. So obviously A is great and G would make you sad down at the bottom. So just before we go, we'll have a quick look at this.
You may have been told that you cannot create or destroy energy, but we certainly use it and pay for it. So what does get used up? It's the usefulness of the energy that gets used as the energy gets dissipated as waste heat. For example, the food mixer transfers the energy carried by the electric current into the movement and sound. The mixer and the food also gets hot. Which of these energies is useful? Clearly, only the movement is useful. The sound and heat are wasted energy. And once the food is mixed, where is the energy now? It's been scattered as the sound is absorbed by the walls, making them a tiny bit hotter, and the warm food mixer gradually cools as its heat is spread into the room. We can also draw it like this. The height of the box represents the amount of energy that's put in. The height of the next box represents the amount of useful energy. The width of any boxes pointing downwards represent the amount of wasted energy. Let's look at light bulbs and work out how efficient they are. First, an old-fashioned filament bulb. Only 5 of 100 joules is useful, so it's 5% efficient. Now LED. 75 joules are useful out of 100, so it's 75% efficient. That's why we are no longer using filament bulbs. Can you calculate the efficiency for this lamp? Efficiency equals useful energy transferred divided by energy supplied times 100. There are ways in which energy transfers can be made more efficient. For example, the use of lubrication can reduce friction and therefore reduce the transfer to heat. The use of thermal insulation can also reduce the loss of heat. A house can be insulated in a variety of ways to reduce heat loss. Insulation can be added to the attic or loft. Double glazing can be used on the windows. Draft excluders can be fitted to the doors. And cavity wall insulation can be used and carpets can be laid. This infrared image shows how heat is lost from a house. The brighter the image appears, the greater the heat loss. Look at the difference adding insulation makes. So this is how we can calculate energy efficiency and make some devices more efficient.
Alrighty, so the last day we looked at this and we said we had to work out some stuff. So in our phone we said our source of energy is chemical. We have said the useful energy from our phone is possibly light and sound, and we said the wasted energy might be thermal energy. We're not interested in that. And we've said sometimes the SEC will use this word dissipated, and that just means wasted energy, so it can be lost usually into your atmosphere. Okay, so we have this now Sankey diagram. So this is really the first bit of note taking, and what they do is they show very accurate energy transfers. Now this is a real rough one. Okay, and just as in the video it shows you, so you're drawing this big ginormous arrow, but it's going to have a part, a turn off to the right, and it's going to have a straight on part. And we have 3 essentially parts to it. So we have the energy input, which is the part down here. We have the useful energy output, which is the part that goes straight ahead. And the bit that clicks down to the right is the dissipated or the wasted energy. So the stuff that's not use to us. Okay, Now, looking at this Sankey diagram, is the amount of useful energy greater, equal, or less than the wasted energy output? So I'm hoping by looking at that particular diagram above, you are saying that the amount of useful energy is greater. So that means this is going to be an efficient piece of equipment if we're going to look at it. Okay, so you are going to make sure you have this taken down as your rag notes. So then we just have this type of scenario. So again, we look at this, and the first thing I'm going to look at is the question down here: is the amount of useful energy greater or equal to or less than the wasted energy? So because this up here is much bigger than this, then the useful energy is greater, so that's going to give you an idea in terms of efficiency. So the energy input we've got here is 10 joules, the useful output is 7 joules, and the wasted energy output is 3 joules. So if you need to now make sure you have put this into your book, because this is one of our examples. So pause if you need to. So if we have to do the piece of maths then that goes with this. So efficiency is the useful energy output over the energy input by 100 over 100%. So the greater the percentage of energy that is usefully transformed, the more efficient it is. So we go back to our little Sankey diagram and we say, okay, if this is very big up here, then compared to this, then we know that this is going to be a really efficient device. So make sure you have the definition, and more importantly, be able to use this when we come to it. So this was our first example. So if I want to find my, we've done this, it's the 10, it's the 7, it's the 3 joules. If we then want to do the piece of maths that goes with this, then it's going to look like this. So the useful 7 over the total energy input 10 multiplied by 100 over 1 is 70%. And similarly then for our bottom diagram down here, you should be able to work out now, is this very efficient? So we're looking at the sizes of this and this. So straight away it's telling me it's not going to be very energy efficient because most of my energy is wasted. And if I do my piece of maths for efficiency, it's 5 over 50, it's only 10% energy efficient. So that is rubbish because you're paying money to input that energy and you're getting only 10% of it back out. Now, you have this in your homework. You're obviously not going to cut these out. We'd be doing these in school if we were. So you would have to do your piece of maths to work out in your homework your percentage energy efficiency for all of these. And you will then put them in sequence of low to high. Okay, so straight away you can tell by looking at them which one is definitely going to be possibly at the bottom. It should be a bit obvious, but you have to do the maths as homework to find out. That's in your homework sheet. Now, we've seen the little basic on the Sankey diagram, but I'm just going to show you this one.
Short video, I'm going to be going through the 5 steps to drawing the perfect Sankey diagram. Before we go through what those 5 steps are, let's just have a quick look at a Sankey diagram just to learn what one is. Sankey diagram has 3 main components. First one being the input energy. That's this bit over here that tells you how much energy is being put into the energy transfer. Second part is the wasted energy output. They're the arrows pointing downwards on our Sankey diagram. And thirdly is the useful energy outputs, which are the arrows pointing to the right on our Sankey diagram. So let's have a go at drawing the Sankey diagram for this kettle. A kettle transfers 800 joules of electrical energy. 600 joules of thermal energy is used to heat the water. 200 joules of thermal energy is wasted to heat to the surroundings. Draw the Sankey diagram to represent this energy transfer. Now, step 1 of drawing your Sankey diagram is you've got to decide on what your scales are going to be. So I've got 800 joules of electrical energy as my input energy here. So I'm going to use 1 square to represent 100 joules. So 1 square equals 100 joules. So that's the scale that I'm going to use throughout this Sankey diagram. Secondly, I'm going to plot the input energy. Now the input energy I've circled, and it's 800 joules. Now remember, our input energy has to be on the left-hand side of our Sankey diagram. And I've got 800 joules. Each square is 100 joules. So the end part of my Sankey diagram arrow needs to have 8 squares. So let's count them: 1, 2, 3, 4, 5, 6, 7, 8. So the start of my Sankey diagram needs to look something like that, where we've got 8 squares. Tick off that bit, because we've just done that bit. Next off, we're going to plot the wasted energy. So the wasted energy here is 200 joules. And it's often easier to plot the wasted energy first. And remember that wasted energy, it needs to point downwards, and it needs to represent 200 joules, which on our scale would be 2 squares. So let's count across. 1, 2 squares there. So this would be part of our Sankey diagram there. Turn it into an arrow. So we plotted the wasted energy outputs now. Next up, what we need to do is we need to plot the useful energy outputs. And before I do that, I'm going to extend the line at the top. And then the end of the line is where my arrow is going to start. And our useful energy output is 600 joules, which is going to be 6 squares on our scale. So 1, 2, 3, 4, 5, 6. So the bottom of our arrow needs to be there. Then we can draw our arrow. Last thing that we need to do is just the last finishing touches. And draw that line up to there and that line up to there. So we plotted our useful output energies. Final thing that we need to do is we need to add some labels to it. And there we have it, there are labels. So let's have a quick summary. The 5 steps to drawing the perfect Sankey diagram. First of all, decide on your scales. Secondly, plot the input energy. Thirdly, plot the wasted output energy. Then plot the useful output energy. And finally, add the labels. I hope you found this video useful, and don't forget to leave a comment to tell me what you think.
Alrighty, so there we had it. So this is our question. For every 100 joules of chemical energy in petrol, only 25 joules are transformed to useful kinetic energy. The rest heats up the engine and the air. We have to work out the percentage energy efficiency, and we have to represent the data in a Sankey diagram. So I'm going to start with the diagram first. So the information we had is 100 joules in. We have 25 joules of useful energy, and we have the rest wasted as thermal. So how do I figure out what's wasted in thermal? I am taking 100, take away 25, gives me 75 joules wasted. So hopefully even just by the numbers you can tell how efficient this particular device is. So we pick our scales, we have 100 joules. I'm going to use 10 boxes for 100 joules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes for my 100 joules. The next thing I'm going to look at is my wasted energy, and we've said that is 75. So 100 joules, we've said 1 box is equal to 10. So it's going to give me 7.5 boxes down. So I just draw here and I count 1, 2, 3, 4, 5, 6, 7.5 boxes. So I draw this down, and obviously you have rulers and you're amazing. So that's my output wasted. I then bring my arrow up here, and my useful energy is going to be worth 25. So I'm going to go 1, 2.5 here. I am going to draw my little arrow here, and I'm going to bring it back. Okay, so that's not as accurate as it would want to be, but straight away you can see this is not very energy efficient. So this is my 25 joules of useful energy. This is my 100 joules input, and this is 75 joules wasted output. Okay, I'm going to put output here as well. So you can see it's relatively easy. Now, if you don't have graph paper or box paper, you can still use the lines in your book to do it. So we've done all of our things. We picked our scale. You could go 100 boxes if you really wanted to for 100 joules, if that floats your boat. But usually the SEC won't give you that much space. Okay, and then in terms of our energy efficiency, then we are taking the 25 joules input, putting it over the 100, which we put in at the very beginning, and that gives me an efficiency of 25%, so not great. And then you are going to now go into your homework questions. Okay, so that is it. I'm on Zoom if you need me. We will see you on Thursday.